Not all bonds are created equal. Some are longer and some are shorter. Some are stronger and some are weaker. So let's look at the principles that determine the strength and the length of a bond. So the first thing that we are going to consider is the size of the atoms that are bonded together. So if you have a nucleus and a really big atom and another nucleus over here, but a smaller atom, right? Then the electrons, if we think about this nucleus and this nucleus, the distance between the nuclei, which is the length of the bond, this distance is the length of the bond. And so the bigger the atoms, the further away the nuclei are going to be from each other. So larger atoms mean longer bonds. In addition, remember that this bond is made up of 2 electrons. And so the longer that bond is, the further away those electrons are from each of the nuclei. And the further away the negative charge is from the positive charge, the weaker that attraction is. Weaker attractions mean higher energy, or less stable, or weaker bonds. So longer bonds end up being weaker because the electrons are further away from the nuclei, not as attracted to them, and therefore easier to pull apart. The other thing that affects the length and strength of a bond is the number of electrons that make up that bond. So if we have a double bond, then we have 4 electrons in that bond. If we have a triple bond, we have 6 electrons in that bond. If we have a single bond, we just have 2 electrons in the bond. And the more electrons in the bond, the stronger the bond is going to be. And because that bond is stronger and there are more electrons there pulling the nuclei, allowing the nuclei to get closer together, we also have shorter bonds. So more electrons result in stronger and shorter bonds. So to be very clear, the weakest bonds of a given type are single bonds. And then the double bonds are stronger than that. And then triple bonds are stronger than that. If we're thinking about length, the longest bond, which is the weakest bond, is the single bond, which is, longer than the double bond, which is longer than the triple bond. So the shortest bond is the triple bond. So I can only compare single, double, and triple bonds between the same 2 atoms or atoms that have comparable size, because both size and number of electrons will make a difference. We use the concept of bond order when we're thinking about the number of electrons in a bond. So bond order is going to be the number of electrons in the bond divided by 2, because 2 electrons make a bond. So a single bond has a bond order of 1. It's that simple. A double bond, double, 2, has a bond order of 2. And a triple bond has a bond order of 3. 3 bonds, triple bond, bond order of 3. The reason we use this concept of bond order is because we have to think about our resonance structures and what that means for the number of electrons that might be in a bond. So if we look back again at our resonance structures for the carbonate anion, and I'm going to leave the lone pairs out, I'm just going to put the bonds in here. We can put that double bond in one of three spots. So it turns out that these two electrons here are not wholly associated with this bond. And they're not wholly associated with this bond, and they're not wholly associated with this bond. So these two electrons are only here sort of 1/3 of the time, here 1/3, and here 1/3. I can only count these two electrons as 1/3 in this bond, 1/3 in this bond, and 1/3 in this bond. So how am I going to count the bond order? Well, I have 2 electrons plus 2 electrons times 1/3, because these 2 electrons are only really 1/3 here. They're 1/3 here and 1/3 here. So this bond order is going to be 2 plus 2 times 1/3 divided by 2. So I have 1 plus 1/3. If I divide both of these numbers by 2, I have 1 plus 1/3, or 1 and 1/3. So the bond order is 1 and 1/3, and it will be the same for each carbon and oxygen bond. This one is 1 and 1/3, and this one is 1 and 1/3, because these are 3 equivalent resonance structures that describe a single structure for the carbonate anion. So in this case, I would say that the bond order is 1 and 1/3 between the carbon and the oxygen, each carbon and oxygen in this carbonate anion. So 1 and 1/3 is bigger than 1, but it's smaller than 2. And so this 1 and 1/3 bond is stronger than a single bond, but weaker than a double bond. It's longer than a single bond, but it is shorter than a single bond, but longer than a double bond. Another way to think about this is that the bond order is the weighted average of all of the bonds in this structure, because this double bond can be anywhere. So I can only do this if I can write resonance structures, equivalent resonance structures. So the weighted average of the bond orders is that 1/3 of the bonds are double bonds, have a bond order of 2, plus 2/3, 1, 2 out of 3, 2/3 of the bonds are single bonds, have a bond order of 1. And so the weighted average bond order is 2/3 plus 2/3 equals 4/3, which is 1 and 1/3. So when I have equivalent resonance structures, I can use the weighted average bond order to figure out the bond order between the carbon and oxygen.